So I'm just going to close the profile. And what I'd like to do now is look at some field result. So to get a field plot, I'm going to go into my modeler tree. You'll see I have a coordinate systems node with my one coordinate there. These planes are also defined in advance. So these are just defaulted values. And as I click on them, they're basically showing the direction of the plane with the given name. I'm going to choose global XY. And as long as that's selected, I can now come into field overlays, and I'm going to right click and choose fields, E for electric field, and I'm going to go with the E vector. And when I do that, I'm just going to go ahead and leave all these defaults and say done. And you'll notice I get a new node that shows up here that we'll probably come back to. I can see my electric field in units volts per meters, and of course you've already seen it show up on the screen with a scale in electric field volts per meters as well. So I want to align the view here so we can discuss this a little bit better. So I can either rotate with my mouse. I can also use the compass here, and notice when it highlights Z for me, if I click, it's going to force the Z axis to be in the normal direction, which is great because we wanted to plot the electric fields in the XY plane. So the electric field certainly exists throughout the whole solution, but it's a lot easier to view just in these cut planes. So let's interpret this. We see the vectors. This makes sense based on what we previously discussed with an analytical model. Notice that most of these arrows, they all appear to be the same color. They're all marked blue if you look at the scale. The arrow is, of course, indicating the direction of the electric field at any given point. If you think of these arrows as having a base and a tip, this particular arrow is basically saying at this point in space, the electric field is going in this direction. If I was to look at this point in space, it looks like it's a slightly different direction, but it's almost the same. Very different than if I go over here, of course. If I choose this location, it's pointed even in a different direction. But it's consistent with the behavior of the electric field from that point charge that we had previously discussed. The mapping of the colors to the magnitude is being done automatically here. So this color scale is assigning the magnitude of the field at the base point of everything that's being shown here. So it looks like they're all bunching around to what appears to be the same value, and that's just because of the defaults with the rendering right now. So somewhere in this field plot, there's a max value of 1.4 times 10 to the 17 volts per meter, and down at the bottom, the minimum is going to be much lower. So 10 orders of magnitude, 10 to the 7th is the value compared to 10 to the 17th. It's a little hard to see. We talked about linear versus log scale before. I'm going to double click this legend. And there's a few different tabs here that we can play around with. The first thing I wanted to do is just go to scale. And I'm going to switch the view from linear scale to a log scale. And this really helps the view a lot more because that wide range of numbers has now been mapped into the same color spectrum, but it's doing it in a log scale. So I would encourage you to play around with the different settings. The rendering sometimes can be greatly improved by taking the time to go through and look at these various things. You can set scale factors, you can set uniformity of vector plots. Some of these can make really big differences in actually what we see. Of course, the results don't change. The results have already been solved, and this is just a rendering. A couple things worth pointing out is that if you remember on our sphere, on our region, when we define this to be a volume of about 500 millimeters on either side, if you remember, we set the conditions so the voltage was 0 on the boundary. Your field results are going to be more accurate towards the center charge than they will be towards the perimeter because we have falsely imposed that condition so that we solve a much smaller volume space. So what you can do is compare your analytical result in regions where it's going to be valid further away from that boundary. It's also worth mentioning that we actually didn't solve for a point charge. Instead, we made a sphere. So if I highlight the sphere, what I can do is choose this Fit Selected option, and it zooms into the sphere itself. I can also highlight the region just outside of the sphere, and I can just hide that from view by hitting this red X. Makes it easier to kind of manipulate our scene here. This shows a very exaggerated looking condition. If I come back into my legend here, I can probably fix this by making my vector plot non-uniform. And if I do that, I go to marker, arrow, and I can bring the scale down. And what you can see is that there is definitely values that have been solved even inside the sphere. So if we are to compare anything that we calculated from this computational solution to our analytical solution, we have to keep in mind what we're actually comparing. So in this example, it wouldn't be valid to choose values that are within the object itself because our analytical model didn't account for that. So I would say a safe value maybe to compare would be, in this example, things that are taking place maybe just outside the surface. So if we compare our 1 millimeter distance from the center of that point charge, I would expect that to compare pretty favorably within the accuracy settings of our computational solver to the analytical estimate. So now I'm going to turn off the vector plot by clicking the node and right-clicking and just turning off plot visibility. So we can always get that back on. The reason I wanted to do that is because now we are going to generate a report. I've got to create an object that I want to calculate the field value on. So before I go to results, I'm actually going to go to draw, and I'm going to choose this point right here. So let's click the point button, and in this view, I'm going to go out to just one millimeter. So 0.7, 0.8, and there's 1 millimeter. So this should be a valid calculation space. If you look in the modeler tree now, I've got under points, I've got this new 0.1. So now I can go to results, and I'll do this over again, field reports, and I'll choose data table, and I'm going to choose the geometry of 0.1. And calculator expression is fine. I want the magnitude of the E field, and with that I should be able to say new report, and I'm going to close this now. If you look in our tree here underneath results, I've got this new called calculator expression table with the element that we just calculated here. So this is indicating that we're at the location of the object we selected, and here I've got the calculated value of the magnitude in volts per meter. If you compare that to the exercise you were given in the analytical portion of this segment, you might remember that the value that you calculated was 8.99 times 10 to the 15. So not exactly the same value, but certainly pretty close if you compared the difference between those two calculations. So I'm going to do this again in a different direction. If I double click my design, it brings this view back present. So let's put another point at 1 millimeter in the Y direction. So I'll choose point, and I'm going to drop it right here. So now I've got my point 2, and I'm going to go back to results, and I'm going to choose another field report, and I'll choose data table. This time I'm choosing point 2, and let's see what we get for magnitude of E field for point 2. And this value, for whatever reason, is closer to our original expectation from the analytical. So if I just go back between these two, I can see 8.85, and the other one is 8.98. So very close. They're the same order of magnitude.